Hello everyone, my name is Anant Saxena and I am an Embedded System Intern at Emertxe Information Technologies. In this video, I am going to present my final internship project, the Real-Time Electric Vehicle Dashboard and ADAS Warning Systems, built on STM32F103C8T6 Blue Pill microcontroller. This project is the result of 1 month of structured hands-on embedded system learning, where I progressed from blinking an LED all the way to building a complete real-time systems with sensor integration, fault detection, UART communication, and Python-based live dashboard. I will first walk you through my presentation slides. Then I will open STM32 and explain the code, and finally I will run a live demonstration on PiximLab with the Python dashboard running in the real time. So let us begin. The prompt title is Real-Time Electric Vehicle Dashboard and ADAS Warning Systems using the STM32F103C8T6 Blue Pill microcontroller. This was developed as my final project during my 1 month internship at Emertxe. The technologies used in this project includes STM32 microcontroller, embedded C programming, Python programming, UART communication, ADC, ADAS algorithms, and HCSR04 ultrasonic sensors. Let us give you a quick overview of what this project does. This is a fully integrated embedded system project that simulates an electric vehicle's core telemetry, an advanced driver assistance system, a fault detection system, and a real-time Python dashboard, all running on a single STM32 microcontroller. The project is built around four major subsystems. The first is the EV model, which simulates vehicle speed, battery, state of charge, motor torque, estimated range, and motor temperature, with three driver modes Eco, Normal, and Sport. The second is the ADAS system, which uses three HCSR04 ultrasonic sensors to detect obstacles in front, left, and right, calculate time of collision, and raise alarm levels. The third is the fault detection system, which monitors critical parameters and identically stops the vehicles when a fault is detected. And the fourth is the Python dashboard, absolutely. A real-time graphical interface that receives all data over UART and display it visually. Now, let me explain the tools and the technologies I used. On the hardware side, I used the STM32F103C8T6 Blue Pill microcontroller, three HCSR04 ultrasonic sensors for the optical obstacle detection, GPIO pins for LED status indicators, ADC analog to digital converter from reading four input channels, UART for signal communication at 115200 watt, and three hardware timers, timer 1, timer 2, and timer 3, each configured for a specific purpose. TIM1 is configured to fire an interrupt every 10 milliseconds, which triggers the EV model update. TIM2 runs a free-running microcontroller counter used by the ultrasonic sensor driver to measure echo pulse width. TIM3 fires every 100 milliseconds, which triggers the sensor readings, ADAS update, and fault check. On the software side, I used STM32 Cube IDE to write all firmware in embedded C. STM Cube MX was used to configure all peripherals graphically. PiximLab was used to simulate the blue pill without hardware, and VSPE, Visual Serial Port Monitor, created a virtual COM port pair so PiximLab and Python could communicate over a virtual UART line. Python 3 was used for the dashboard with Matplotlib for real-time plotting and PySerial for UART reading. As you can see, it is the STM32 IDE IOC file configuration. Now, this slide shows the complete system architecture. Data flow through the system in a pipeline. It starts with driver inputs, four potentiometers connected to PA0, PA1, PA2, and PA3, representing the acceleration pedal, brake pedal, initial SOC, and motor temperature. These are read by STM32 ADC and fed into the EV dashboard for physics computation. The ADC engine runs in parallel, reading distance values from three HC SR04 sensors and computing collision warnings, blind spot detections, and time of collision. The fault detector monitors critical thresholds and sets fault flags which control the GPIO LEDs. The UART shell formats all this data into two compact lines and transmits it every 100 milliseconds. And finally, the Python dashboard receives this data, parses it, and updates the graphical display in real time. The entire system is given by timer interrupt, which makes it deterministic and real time. TIM1 triggers EV read ADC and EV update every 100 to 10 milliseconds. TIM2 runs free to microseconds ultrasonic timing, and TIM3 triggers the full sensor to fault pipeline every 100 milliseconds. This slide shows my learning journey through the internship. The training was structured into 7 modules, and each module taught me something. Module 1, GPIO and LED blinking. This was my first hands-on experience with the STM32. I learned how to configure GPIO pins as output, understand push-pull configuration, and use HAL GPIO right pin to toggle a LED. Module 2, hardware timers. I configured TIM 1, 2, and 3 with specific periscales and periods to generate precise time intervals. I learned about period eclipse interrupt callbacks. Now, Module 3, the ADC. I configured a 12-bit ADC to read 4 channels, acceleration pedal on PA0, brake pedal on PA1, and SOC seed on PA2, the motor temperature on PA3. Now, the Module 4, UART communication. I configured USART1 at 115200 baud with interrupt-driven receive using HAL UART receive IT. I built a ring buffer and interactive shell to send and receive commands over serials. Module 5, single HCSR04 ultrasonic sensors. I implemented the complete trigger and echo protocol using TIM2 as a microsecond counter and calculated distance from echo pulse width. The module 6, the HCSR04 sensor, I explained to 3 sensors, front, left, and right, with a 50 millisecond inter-sensor delay to prevent ultrasonic crosstalk between sensors. And final, the module 7, complete integrated systems. This module combined everything: ADC, UART, GPIO, timers, 3 sensors, EV models, ADAS, fault detection, and the Python dashboard, all working together as one complete embedded system. Now, let me explain the EV control module in detail. The EV model is implemented in evcontrol.c and runs every 10 milliseconds triggered by TIM1. The computation pipeline works in 7 steps. The step 1, ADC reads. The function EV ADC reads all 4 ADC channels and maps them in physical value. PA0 maps to the acceleration pedal 0 to 100%. PA1 maps the brake pedal 0 to 100%. PA3 maps to the motor temperature 0 to 120 degrees Celsius. Now the step 2, motor torque. Torque is calculated as torque equals accelerator percentage divided by 100 multiplied by the maximum torque of 150 newtons meter multiplied by the drive mode scale factor. Now the step 3, regenerative braking. If the brake pedal is pressed harder than the accelerator, regenerative braking is activated and motor torque becomes negative. Speed using Euler integration, acceleration equals net torque minus drag divided by the mass factor. Speed is updated every 10 milliseconds using the accelerator. The step 5, power in kilowatts. Mechanical power equals torque multiplied by velocity. The step 6, SOC drains. State of charge decreases proportional to the power consumed. Step 7, range estimation. Remaining range is calculated by the current SOC and drive mode efficiency in WH per kilometer. The 3 driver modes scale the maximum torque. Eco mode uses 60% of the maximum torque for efficiency. Normal mode uses 100%. Sport mode uses 130% for maximum performance. The vehicle state machine ensures correct behavior. The vehicle starts in parked state, when the accelerator is pressed above 2%. It transitions to ready, then to driving. If the brake is pressed above 5%, it enters Region mode. Any fault condition immediately puts the vehicle into the state fault state, cutting motor torque to zero. And this is the complete Pixim Lab simulation in the spare part section of brake pedal, acceleration pedal, SOC temperature, and all the other ultrasonic sensors with the LED accumulation. Now, let me explain the ADAS Advanced Driving Assistance System. The HC-SR04 ultrasonic sensors works like this. I send a 10 millisecond trigger pulse to the trigger pin. The sensor then emits 840 kHz ultrasonic pulse. The echo pin goes high for the time it takes the second to return. Distance is calculated as echo time in microseconds multiplied by 0.0343 divided by 2 in centimeters. I have three sensors. The front sensor trigger on PB0, echo on PB1. It provides forward collision warning below 50 centimeter in the warning condition. Below 20 centimeter is a critical condition. The left sensor trigger on PB2, echo on PB3. It provides blind spot detection on the left side. If distance is below 30 centimeter and the vehicle speed is above 20 kilometers per hour, the left blind spot alert is activated. The right sensor trigger on PB4, echo on PB5. Same logic as the left sensor but on the right side. Time of collision is calculated as front distance in meters divided by the vehicle speed in meters per second. The system has four alarm levels: none, no obstacle, advisory, blind spot or overspeed, warning, find obstacle below 50 centimeter or time to collision below 3 seconds, critical, front obstacles below 20 seconds or time to collision between 1.5 seconds. A hysteresis counter of 3 samples prevent rapid toggling of alarm. This slide covers two important subsystems, the fault detection system and the UART interaction cell. The fault detection system monitors three conditions every 100 milliseconds. Fault OT, motor overheat. If motor temperature reaches or exceeds 90 degrees Celsius, this flag is set. The vehicle enters state fault and the fault LED on PB11 turns on. Fault SOC, low battery. If SOC drops to be below 2%, this flag is set with the same consequence. Fault collision, collision critical. If its confirmed critical collision warning is active, the flag is set. When any fault is active, motor torque is immediately set to zero and the vehicle cannot move. And the fault LED provides visual indications. The fault can be cleared using the fault clear command, which resets all the flags and returns the vehicles to the parked states with safe default. Now, the UART shell. This is an interactive command interface I built using a ring buffer and the interrupt-driven UART receiver. The output format is two compact lines transmitted every 100 milliseconds. Line 1 shows speed, SOC, torque, motor temperature, range, accelerator, brake, and driver modes. And the line 2 shows front distance, left distance, right distance, time to collision, collision warning, blind spot status, alarm level, and fault flags. This shell also accepts command for live testing without changing hardware. For example, fault inject motor artificially raises motor temperature to 95 degrees to test the overheat fault. Obstacle 15 overrides the front distance by 15 centimeters to test the critical collision alarm. Fault clear resets everything back to the normal. Now, the Python dashboard is the final display layer of this entire system. The communication pipeline works like this. PiximLab simulates the STM32 and the outputs UART data to COM14. VSPE connects COM14 to COM11 as the virtual serial port pair. The Python script opens COM11 using PySerial and reads incoming UART line in the background thread. The main thread redraws the matplotlib dashboard every 100 milliseconds using Func animation. The dashboard has 5 panels. Panel 1 is speedometer, an arc-shaped gauge display 0 to 200 km per hour. The arc color changes from green below 100 to orange below 140 and red above 140. The needle points to the current speed by a digital readout below. The panel 2 battery panel Shows current SOC as the percentage with the progress bar, estimated driving range in kilometers, and the current driver mode, eco, normal, or sport. Panel 3 is speed history graph, the 60 sample rolling line chart showing speed over time. This updates every 100 milliseconds, giving a visual history to how speed has changed. Panel 4 EV meters panel. The table shows torque acceleration, brake motor temperature, alarm status, fault code, and signal status. The panel 5 ADAS bird eye view. The top down view of the vehicle showing the EV vehicle blocks in the center. The front obstacles as the colored block which moves closer as the distance decreases, an arc between the vehicle and the obstacles that turns red when collision is imminent. Left and right blocks of the blind spot alerts and the time to collision display at the bottom. This is the complete representation of the EVADAS dashboard that we have talked earlier. Let me now share what I learned from this internship. In the area of embedded C programming, I learned how to use the STM32 HAL library for peripheral configuration. I gained practical experience with interrupt-driven programming, both for UART receivers and timers callback. I learned about volatile variables and why they are essential for safe communication between ISR and main loop context. And I learned how to structure firmware into separate .c and .h files to clean modular architecture. In the area of timers and ADC mastery, I configured three timers with different periscales and periods. For three completely different purposes, I learned 12-bit ADC polling with dynamic channel switching. I achieved microseconds precision timing from ultrasonic sensors measurement, and I calculated pre-scalars and period values from scratch to receive exact time intervals. In the area of sensor integration, I implemented the complete HCSR04 trigger and echo protocol from scratch. I solved the ultrasonic crosstalk problems by adding a 50 millisecond delay between sensor readings. I computed time to collision in real time and I designed a hysteresis system to prevent false alarms from rapid state toggling. In the area of system level thinking, most importantly, I learned how to integrate seven individual modules into one complete working system. I designed a state machine for realistic vehicle behavior. I built a UART shell to live injunctions and testing without hardware changes, and I connect the embedded systems to Python for real-time data visualization. To conclude, over the course of this 1 month internship at Emertxe, I successfully built a complete real-time electric vehicle dashboard and ADAS warning system. I completed 7 structured modules, integrated 3 HCSR04 ultrasonic sensors, built an EV physical mode and 3 driver modes, implemented a 4 condition fault detection system, a connected everything to a Python dashboard displaying more than 17 real-time matrices. This internship gave me my very first real world embedded system project experience, from a reading data sheet to writing to the drivers, all the way to building a complete product that works end to end. I am grateful and very thankful to Emertxe Information Technologies for providing this structured, practical, and industrial standard curriculum. Now I will move on with the live demonstration. Please watch carefully as I run the full system in the real time. Now, I will open the STM32 IDE and walk you through the project structure. This is the STM32 IDE workspace for my project named EV Dash. You can see the project structured in the left panel. Under, under core, there is the source folder and the include folder. All my firmwares are present here as we can see. Now, this is the CubeMX configuration file ev-.ioc which we have opened presently. Okay, the pin highlighted in green are configured as GPIO output. The pins in blue are ADC inputs. PA9 is configured as USART1TX and PA10 is USART1RX. PBO is the trigger for the front ultrasonic sensor. PB1 is the echo input. Let me quickly show the peripheral configuration as well. Now, when coming to the timer 1 configuration, as we can see, the timer 1 is configured with parascale of 71, which divides the 72 MHz system clock down to 1 MHz. Period of 9999, which means it fires every 10 milliseconds. This gives us our 10 milliseconds EV ticked. Timer 2 is configured as a free running counter, as we can see here. This gives us a microcontroller resolution for ultrasonic timings. And timer 3 is configured with the prescalar value of 7199 and the period of 999. 7200 times 1000 equals 7.2 million ticks, which at 72 megahertz gives equal 100 milliseconds. This is our sensor update tick. Now let me take you through the main.c code of my EV ADAS code. This is the entry point of the entire firmware. At the top, you can see all the modules header includes evcontrol.h, ultrasonic.h, ADAS.h, fault.h, and the UART shell.h. The three global handlers are declared here. EV handle type def, ADAS handle type def, and the fault handle type def. These two volatile flags are critical. Flag EV is set by time 1, interrupt every 10 milliseconds, and the sensor flag is set by time to interrupt every 100 milliseconds. This must be declared volatile because the compiler must not optimize away reads from these variables, and they are modified inside interrupt service routine. Now let me take you through the timers. Yes, this is the timer period ellipsed callback. When TIM1 fires, flag EV is set to 1. When TIM2 fires, sensor flag is set to 0. These flags are connected in the main loop. Now let me take you to the while 1 loop. Yes, we can see in the while 1. This is the main loop. Every 10 milliseconds when flag EB is set, we clear the flag immediately. We call EB read ADC to read all 4 ADC channels. We call EB update with the time step of 0.01 second. Every 100 tick, which is 1000 milliseconds, we call shell print status to permit the current status over UART. Every 10 milliseconds when sensor flag is set, we clear the flag. We call HC SR04 read all to read all three sensors. We call ADAS update to complete collision and blind spot status. We call fault check to evaluate all fault conditions. And we call shell underscore process to handle any incoming UART conditions. Now let me open the evcontrol.c code. Now, let me show you the evcontrol.c as we are in the screen. The read ADC channel functions configures the ADC dynamically to read any channel by software. It starts the conversation, polls the completion, and returns the raw 12-bit value. The EV read ADC function reads three channels: accelerator at PA0, brake at PA1, and temperature on PA3, and converts them to percentage and temperature values. The EV update function contains the core physics. Notice the state machine switch statement at the top. The state pegged. In the state pegged, torque is 0. If accelerator is pressed above 2%, it transmits to ready. The state driving. In state driving, if brake exceeds the threshold, it goes to a region. In state fault, torque is immediately set to 0 and the function returns. The speed update use Euler's integration. Acceleration equals net torque minus drag divided by mass factor. Speed is updated as speed plus acceleration times time setup 3.6 to convert to the kilometer per hour. Now let me take you to the ADAS.c code. The HCSR04 read function in the ultrasonic.c sends the trigger pulse, wait for echo high, measures the high duration using TIM2, then calculates the distance. The ADAS update function gets distance from all three sensors, computes time to collision, evaluates collision and the blind spot conditions, and set the alarm priority level. Notice the hysteresis check function. We have to notice specifically the hysteresis function. It uses the counter to keep an alarm active for a minimum number of cycles before it can clear. This prevents false alarm from sensor noise. Now, we should briefly go to the fault.c code. Fault check evaluates three conditions: the set flag bit and the fault handle. If any flag is set, the vehicle state is immediately forced to state fault. The fault LED on PB11 is turned on. Fault clear resets everything: flag, speed, torque, and temperature, and returns to state peaked. Now coming on the UART shell.c code. The shell print status function formats and transmits two lines. Line 1 contains all EV data and line 2 contains all ADAS and fault data. The shell process function reads from the ring buffer, echo each character back and process complete commands when enters is pressed. The command parsers handle all test injection commands using the scanf for flexible parsing. Now it's the real time, the time to build the project. We have to build the project as we have to click the file explorer and right click the project explorer of the project we are in, and we can create build project and we will have our configured build, and we will see that there is no warning as well as there is no error. Now it's time for the live demonstration in the PixSimLab simulation. So coming on to the PixSimLab. PixSimLab allows me to run the STM32 binary file as a physical hardware. It simulates all peripherals, includes the GPIO, ADC, UART, and timers. Now we can simply load the binary file and we will have our outputs in the spare parts section. In the spare parts section, we would, in the spare parts section, we have it. Now I will show you all the visual components connected in STM32, 4 potentiometers on PA0 through PA3, labeled as acceleration pedal, brake pedal, SOC, and the motor temperature, 2 HCSR04 sensors for front and left distance, one more HCSR04 for the right. The GPIO LEDs for collision, blind spot, and fault detection, and the virtual terminal for UART. Now let me open for you the virtual terminal. We can see, look at the line 1. Now the line 1 starts to generate speed, SOC, torque, temperature, range, accelerator, brake, and driver modes. And the line 2 shows front distance, left distance, right distance, time to collision, collision warning, blind spot, alarm, and fault. Everything is updating every second. Speed is currently at 30.9 because the acceleration potential PA0 is set to a particular bench. Now I can show you the VSPE tool. Here VSP is already configured. COM14 is the virtual port connected to PixSimLab, and the COM11 is the port used by our Python dashboard. VSP bridges these two ports so data flows from STM32 to the Python. Now it's the real time to open the Python dashboard in the command prompt. So now let me launch the Python dashboard. I will now open the command prompt and run the python ev-py command. The dashboard window opens and you will see all panels are live. The speedometer, battery panel, EV matrices and the ADAS bird eye view. Signal shows on, which means UART data is being received. Now let me go again to the Pixim lab and do some changes in the configuration. Now I would like to press the accelerator. I am moving the PA0 slider upwards. Watch the virtual terminal, the speed value is increasing. As we see the virtual terminal, the speed value is increasing at a greater speed. The acceleration percentage in the EV matrix panel is increasing. SOC is slowly decreasing as energy is being consumed. It is a complete EV model running in real time on the simulated STM32 Cube IDE, as we can see in the dashboard as well, and the speed is increasing. Now, I would like to release the acceleration and apply some brakes. Okay, I am moving PA0 back down to 0 and accelerating it and applying the brake. Now I am moving P0, the brake pedal upwards. The region state is now active. Speed decreases faster, motor torque shows a value reflecting regenerative braking, as we can see it in the virtual terminal as well and in the Python dashboard. Also the speed is braking and is getting down. Now, let us demonstrate the ADAS collision detection. I will first increase the acceleration to build up some more speed for approximately 50 to 60 km. I will move the front HCSR04 distance down to simulate an obstacle detection. For example, till here. Now, watch the terminal. We should watch the terminal now. We can see that at 50 centimeters a warning is triggered. The alarm shows warning. The collision LED on PB8 turns on, moving it below 20 centimeters. Now it shows critical in the EV dashboard. As we can see, it is critical in the EV dashboard. The dashboard background flashes red. This is the critical collision alert. Now, moving the obstacle away, alarm gets to none. We can see in the virtual terminal, the alarm gets to none and we can see different values. Now I will demonstrate to you the blind spot detection. Okay, so in the Pixim Lab simulation only, I am moving the left sensor sliders down by 30 centimeters. By 30 centimeters, while the vehicle speed is should be approximately 20, we should decrease the speed so that it reaches 20 at any moment and we will receive our desired value and we would be able to see it in the ADAS dashboard also, as we can see in the ADAS dashboard what we were waiting for. Now let me demonstrate the fault injection. I will now use the demonstration to see you the motor temperature at 95 degrees Celsius or above. Clearly watch what happens. More temperature. If it jumps by 95 degrees, fault OT is set and the fault flag shows 0x01. The vehicle enters state fault. Motor torque drops to 0. Fault LED on PB11 turns on, and even if I push the accelerator now, speed does not increase. And the speed does not increase in this case at all, as we can see it here. Now it's time for the conclusion of my Python dashboard. To conclude the live demonstration, you have just seen the complete real-time electric vehicle dashboard and ADAS warning system running end-to-end, from the STM32 microcontroller running embedded C firmware through UART communication over the virtual serial port to the real-time Python dashboard displaying live speed, battery, distance, alarm, and fault status. All of the sensors, state machines, physics model, fault detection, UART communication, and live visualization running together on the single STM32F103C8T6 microcontroller. This project has been one of the most valuable learning experience of my engineering journey so far. I started this internship through how to blink an LED. I am ending it with a complete embedded system product. I want to thank especially Emertxe Information Technologies for their structured curriculum